Hello and welcome to BitGardener's Office Hours. My name is John Kowalski. I'm part of the marketing team here at BitGardener. And if you're unfamiliar with our Office Hours format, we will begin with a shortened presentation, maybe 20-25 minutes or so. Then it will be opened up for your questions to have discussions to address any challenges you may be having at your facilities. So please enter in any questions you have in the chat function, and we'll get to them in order. Also, we are recording this, and immediately following the presentation, you'll be receiving an email with that link. So feel free to reference it, watch it at a later date, share it with colleagues, or use it for date night, whatever you need. So with that, let me introduce our Senior Applications Specialist, Mr. Corey Cohen. He'll take it over and talk about elliptical tolerancing and the evolution of color difference equations. Thank you.
Thanks, John, and good afternoon, everyone. Thanks for joining us. So today's topic is on elliptical tolerancing and color difference equations. As usual, this will not be a thorough or complete overview of the topic. This is going to be just enough to sort of whet your appetite, give you just a general idea of what we're talking about here, and then we're going to take some questions, and you guys can kind of steer the conversation. So to begin with, just want to make sure you're all familiar with this LAB space, CIELAB space, it's sometimes called. And the LAB system is just a three-dimensional coordinate system where you can describe any color using these three values, L, A, and B. L is for lightness. The higher the L value, the lighter the color. The A value tells you how much red or green is in your color. A positive red value tells you there's red in the color. A positive A value tells you there's red in the color. A negative A value tells you there's green. And for the B axis, positive B indicates yellow and negative B indicates blue. So that's the CIELAB system. And here we have an example of a color. L equals 58. A is positive 30, so that's a good amount of red in the color, and B is positive 36. That's a good amount of yellow. So we have a lot of red and a lot of yellow. So we're getting an orange color here. And so when we measure colors and we get our LAB values, usually what we're really interested to know is what is the difference between two colors, specifically sample and standard. So standard is your target color. It's the one you're trying to match. And you want to know how far off from that standard is your sample. The way you do that is you take these difference values. So you can take the difference in the L value, the difference in the A value, the difference in the B value. And this tells you a good amount of information about the difference between these two colors. Is the sample lighter or darker? Is it redder or greener? Is it bluer or yellower? But ideally what we want is to have one number that can tell us the overall color difference between these two colors, between the sample and standard. One number that we can say that number is too big, or it's within tolerance and it's a pass or a fail. And that number is the delta E. So here we have an equation for the delta E star value. And this is the simplest calculation for the overall color difference, and all it is really just a distance formula in the CIELAB space. So what you're doing is you're going to take the difference in the L value squared, add it to the difference in the A value squared, plus the difference in the B value squared, then square root the whole thing. Really all that is you're just finding the distance between these two colors in this LAB color space. Here again, we have our LAB color space, but now here we're being given coordinates in LCH. Now LCH coordinates, they're just like LAB. They describe a color in the same color space, the same CIELAB coordinate system, but it's just describing the color slightly differently. So instead of having an L value, an A value, and a B value, those rectangular coordinates, this would be sort of the polar coordinates version of that. And what we have is so the L value is the same. It's the lightness axis. The C value is for chroma, and that tells you basically how colorful your color is, or how saturated. Sometimes that term is used, saturation. So chroma tells you how much color is in your sample, and the higher the C value, the more chroma. So a very chromatic color would be something like a scarlet red or a forest green, or something like that, whereas an achromatic color, a color with a very low chroma value, would be like a neutral, like a gray, or maybe an off-white, like a beige or something. So we have L, we have C, the chroma value, and then we have the hue angle. And so the hue angle tells you the hue of the color, red, yellow, green, blue, or any of the intermediate colors in between. And it gives that, it expresses it as an angle on this AB plane. So the positive A axis, if you look in the positive A direction, that red axis, that's 0 degrees on this wheel. And if you count up as you go counterclockwise from there, so you'll get to the yellow axis, which is 90 degrees. Continue counterclockwise, you get to the green axis, which is 180 degrees. The blue axis is 270. And so you describe your color by the hue angle on this color wheel. So for example, this hue angle we're seeing here is 38 degrees. Now we know 0 degrees is the red axis, 90 degrees is the yellow axis, so we know that hue angle lies somewhere in between. So somewhere between red and yellow, again, we know that's an orange color, right? So this is the same exact color as this, it's just using different numbers to describe it. Okay, so that's LAB and LCH, and there's a reason we have two different coordinate systems, and it has to do with the way we tolerance colors. And so for non-chromatic or achromatic colors, those are the ones with very low chroma values, your grays, beiges, what have you. And those non-chromatic colors are defined as any color with a chroma value less than 10. And in that case, we recommend using LAB tolerancing. If the chroma value is larger than 10, if it's a chromatic color, we recommend switching to LCH tolerancing. And I will explain why that is right now. So here we have a number of production samples that were visually evaluated against the standard. And then all of those colors were measured and graphed or mapped in this AB space, right? So we have that double triangle symbol in the center. That's our standard. And then each of those circles, whether it's the gray circle or the one with the red X, those are different samples and where they exist in relation to the standard, right? And so those were sorted into visually acceptable and visually unacceptable. And so the gray circles are the visually acceptable samples, and the ones with the red X's are visually rejected, right? So those are the ones that are a bad color match. And so when you tolerance this standard, so this is, by the way, the proper recommended procedure for figuring out what your tolerances should be. You take a large number of samples and you visually evaluate them as acceptable or unacceptable. And so here, when you want to set the tolerances, you set the tolerance on the A value and on the B value, and you can also set the tolerance on the L value. That's not shown here. But what you end up with is this square or a cube, and this is what we call box tolerances. So when tolerance on the LAB values, that's called box tolerances. And that's pretty good for this case, for this achromatic color, where this visual tolerance shape, if we take all of our acceptable samples on this AB plane and we draw a shape around them, we get approximately a circle or a sphere if we're talking in 3 dimensions. So this box, these box tolerances work pretty well to approximate that, that circle that we naturally get when evaluating these samples visually. So LAB tolerancing is pretty good for achromatic colors. So now we're looking at a chromatic color, and it looks a little bit different. So the same thing was done. You took a standard, you took a bunch of production samples, and these were sorted into visually acceptable or visually unacceptable, and then mapped here in this A-B plot. And we see now if we draw a tolerance shape that encompasses all of those visually acceptable samples, we get approximately an ellipse rather than a circle like we had before. And so if we try to apply tolerances to this, let me make sure my pointer is going. All right, so hopefully you can all see my pointer. So if you tolerance it such that it only, that tolerance box only encompasses all the visually acceptable samples, excepting this little outlier here, you get this really small box. And so what you're going to end up doing is rejecting a lot of these samples that are out here and don't fit into that nice, neat little box. So what you can do is, of course, you can increase your tolerances. You can make that box bigger so that now you're accepting all of these samples that were found to be visually acceptable. But now you're also accepting a lot of samples that have been rejected. So now you're going to be shipping a lot of product that doesn't actually look very good. So neither of those things are ideal. And this is why, for these cases, for chromatic colors, we like to switch to LCH tolerancing. Because now instead of tolerancing in the A and the B direction, which forms this box with this particular orientation, now we're tolerancing on the C value and on the hue angle. And so that, by its nature, because the hue angle is always going to point towards the direction of the color, it's going to create this sort of pie slice shape, and that shape is better oriented towards this ellipse than those box tolerances were. And so this is why we recommend using LCH tolerancing for chromatic colors, because the LCH tolerances create a shape that fits the visual tolerancing better. So that leads us to our delta E value. So here we have an example. We have two samples here, and those are being compared to a standard. And so sample 1 was measured against the standard, and the delta E was calculated, and sample 2 was measured against the standard, and the delta E calculated. Now we can see in sample 1, the delta L, delta A, delta B values are all the same. So those color differences between the sample and standard were sort of split evenly across those three axes, the lightness, the A, and the B. Whereas, and the calculated color difference is, of course, 1, as we can see here. So for sample 2, though, we can see that the differences were not evenly split across L, A, and B. We can see that the L value is right on. The B value is exactly the same. It's only the A value where you're getting all the difference, a difference of 1. And so that's going to result in a delta E value also of 1. But if we look at these samples visually, compare sample 1 to the standard and then sample 2 to the standard, it's not even close. Sample 1 looks visually way, way closer. So this is just sort of to illustrate why delta E is not always the best way to do things, because these calculated color differences under the delta E star equation, this equation right here, you can get the same differences, the same calculated differences between two colors that look visually very, very different. So what we want is improved color difference methods that will make it so that all colors have the same tolerance. And here we have another slide to illustrate that point. And so here we're seeing again a slice of color space, the AB plane. And we have, of course, you have your more chromatic colors towards the outside of the circle and the less chromatic colors towards the inside. And you see all of these shapes drawn on this wheel, these little ellipses. And these are visual tolerant shapes. And so in the middle of each shape, you should be able to make out a tiny little dot. So that is the standard for each shape. And the shape gives you the visual tolerance. So the idea is that any other color existing inside the shape would be visually indistinguishable to the standard, right? Our eyes can't tell the difference between this standard and any other color inside that ellipse. But we can see that these ellipses, these tolerance shapes, they vary as we go to different spots on this color wheel. For example, tolerances are tighter for achromatic colors than they are for chromatic colors. They tend to be, chromatic colors tend to have larger tolerances than achromatic colors. Tolerances tend to be tighter for hue than for chroma. That's why these have an elliptical shape, because they're longer in one direction, in the chroma direction, than they are in the hue direction. And the size and the shape of the ellipse can depend on the actual hue. So different colors actually have different acceptability. For example, you can see these green tolerance shapes to the left tend to be significantly larger than most of the other ones and the other parts of this color space. So the hue of the color can actually affect the tolerance. So this is why improved color difference equations were developed to provide better agreement with visual color perception, with the overall goal of having one tolerance for all colors, meaning a uniform color space. Meaning, so if you produce, say, a green and a red color, under the delta E star system, if we're looking at this color wheel, the green color might have an acceptability of a delta E of 3, and for the red color, it might only be 1. So you don't want to have to determine tolerances for every single color that you produce. You just want to have one tolerance and trust that that's going to match up with what we see visually, that the numbers for one color will match up with the numbers for another. So I chose just one method to kind of go into in the interest of time here, and that one is the delta E94 equation. So this was based on visual evaluation of new sample sets using solid colors. These are solid colored glossy painted panels, currently published in the following CIE recommendation. It's based on elliptical spacing and delta LCH. And it corrects only for chroma-dependent perception of chroma and hue with no lightness correction. So here's what that equation looks like, and sort of generally what any color difference equation is going to look like. You have the delta L, C, and H terms, and then in the denominator you have some sort of scaling factor, the SL, SC, SH terms, which are dependent upon the standard's position in color space. So these tolerances, the overall delta E number that you're going to calculate under this equation, is actually going to depend on where the standard is in color space, which is the whole idea. There are also these application factors, KL, KC, KH, that can correct for variations in reference conditions such as the illuminant or the light intensity. And so by switching from delta E tolerancing to delta E94, rather than having this box tolerance like we're seeing on the left, we're getting this elliptical tolerance, which we can see better fits our visual acceptance. And in addition to that, it's going to sort of scale that delta E value differently. If you look up in the data table at the delta E values under delta E star, they're all fairly large. But what was found under this delta E94 equation is that they're sort of artificially large. The visual color difference is not as large as it is, as it sort of seems under the delta E calculation. So under delta E94, which correlates better with our visual perception, those numbers go way, way down. And whereas with delta E star, all of these colors were out of tolerance, under delta E94, they are not. Okay, and I just wanted to mention real quick before we finish that there are also improved difference equations specifically for multi-angle color measurement for colors with effect pigments where the appearance is going to change from angle to angle. So like automotive type coatings and things like that. And one of the biggest differences with these types of equations for multi-angle is that the equation is dependent on the angle. So this gamma symbol here that you see in the parentheses, that represents the angle of measurement. So this will be calculated, 6 times or however many different angles you're measuring it at. And it also chooses an equation, chooses LA or B tolerancing or LCH, depending on whether the color is measured to be chromatic or achromatic, and it will select the right one for each angle. In addition, the difference methods for effect colors also have these application factors. That's what these G factors are here in the denominator. And that's for different applications require different tolerances. For example, testing an incoming batch of paint or colorant would have tighter tolerances than for on a repair line. And so these G factors account for that and sort of tighten or loosen the calculation depending on the application and how tight you need the tolerances to be. So that is all I have prepared for you. I will toss things back to John and let's get some Q&A going.
Great stuff as always. If you have questions, comments, if you'd like some additional clarification on anything, please log it in the chat area and we can get to it. We have, a fair amount of time left. So this time is yours. How can we help? How can we assist? While folks are thinking about that and hopefully, writing in some questions here, Corey, are there frequent questions that you get around color equations or specific challenges that, tend to be a trend?
Probably the most common one I get having to do with color equations is which one should I use, which is certainly a fair question.
And that really depends on the application, correct?
Absolutely, yeah. So different equations were developed using different sample sets. For example, the last equation I went over for effect colors was developed by visually evaluating samples with metallic pigments in them, with effect pigments in them. So that's part of the reason that one's best for effect colors is it was developed using evaluation of effect colors, whereas there's an equation called delta E CMC for solid colors, but that was developed using textile samples. So if you're doing like low gloss or textured or, of course, textiles, CMC might be the best one for you. If not, it might be 94 or delta E 2000, which were based on solid colored painted panels.
Okay, yeah, that makes sense with all the different markets and applications out there. Definitely, it's going to vary. Got a question here. Sorry, I missed. Which was set up for metallic and effect pigments?
Which was, I'm sorry?
Which was set up for metallic and effect pigments? Which color equation?
So the name of the equation that most of them were based on, it's called DIN 6175 Part 2. DIN 6175-2. And so, yeah, that was the evaluation of those effect samples and all that was in service of developing that equation. And then there have been a number of equations that we've sort of developed or sort of just slightly modified the DIN equation to meet the specifications of various automakers. So we actually work with the automakers directly. And so if you look in our instruments or in our software, you'll see equations for delta E GM, delta E Kia, things like that. but they're all based on DIN 6175-2.
Okay, great. Joni, did that answer your question? You can type it in. She's asking, oh, yes, it did. Thanks. Good. Also, follow-up question, is the DIN 6175-2, does that require a multi-angle spectro?
Yes, it does.
Okay. Good. Just due to the nature of the effect pigments.
Yep.
Good, good. Excellent. Other questions out there, or specific challenges you're having in your facility? We have the time. Corey's our applications expert here. We have also some people from our field team on the line. They can help, and Mike, Stephen, feel free to chime in too if you have any frequent questions you guys get. You're able to unmute yourself on your end. Question from Barbara: are there difference equations for XY color systems?
Are there difference equations for XY color systems? Not really. So it all comes back to the tri-stimulus values, X, Y, Z. The LAB and LCH values are calculated directly from the XYZ values. And of course, these difference equations utilize the LCH and LAB values to calculate the delta E. So it all sort of follows one from the other, but there's nothing specifically for XY color space, no.
Okay. Did that answer your question, Barbara?
Barbara, if you're having difficulties with tolerancing, or you maybe want to talk about your specific application, well, I mean, you can feel free to ask now, of course, but we could always connect offline if you want to. Yeah.
She did chime in. We have to use the ASTM standard D6628-16 standard specification for color of pavement marking materials.
Okay. Pavement marking materials definitely sounds familiar. I've definitely dealt with some like DOTs doing stuff with that. As far as this specific ASTM method, that's going to take some research. So I am going to have to ask you to maybe contact me offline when I have some time to look into that for you.
Great. Thanks, Corey. Thank you, Barbara. Another question here. Let me read. I'll be doing weathering analysis of our clear over laminates applied to a white film. We have listed yellowness index and delta E plus. We do, let me start that sentence again. We have listed yellowness index and delta E, plus we do visual analysis also. Which delta E equation works best for clear film over white? We will use the Spectro 2 Guide Pro unit to analyze the samples, 450.
I'd say Delta E2000 would probably be best for that.
Okay. Does that answer your question, Nilo? And two, if anyone has a complicated question, just ping me to unmute you, and I can unlock your microphone from my end. Then you can unmute yourself and address the group and Corey specifically. Oh, great. Glad that helped, Nilo.
If you slip John a 10, he'll unmute you just a little bit quicker.
Exactly. If you're unruly, I'll mute you for good. So what other questions out there do you guys have that we can assist with? And this, this specific topic around equations and tolerancing, that's the focus here. But if it's something in the realm of color appearance or physical test, we can also, field any of those questions too. And if always too, any of these autoresponders for this meeting, feel free to respond. They'll come to myself or my marketing colleague, and we'll get them to Corey or the appropriate regional manager. So lots of opportunities. Just want to help you out and alleviate some pain or challenges if we can, to make things run smoothly, keep your quality up and your efficiencies up. Quiet group today. Mike, Steve from the field, you guys get any specific questions around color difference equations or tolerancing? Anything else, folks? Other questions that you get, Corey, around this? I know it's specific to each application, but are there any kind of nuances to certain industries or markets that, you know, are just kind of stranger out there?
Probably. Yeah, I mean, the important thing is really just to, whenever you have to communicate values or report values, it's always very important. I'm going to use a term that we just beat to death, but always compare apples to apples. So if you're using, Delta E, CMC, or 94, or what have you, and you need to compare your results with a customer or a supplier that is also taking color measurements, they need to be using the same difference equations so you two can match up and get consistent results.
Okay. What about when it comes to deep colors looking similar or tolerances that should be set up differently?
So the whole
that was a big sigh.
I mean, the whole idea of basic. Oh,
what was that? You're there.
Am I back?
You're back. You're back. Yeah. So sorry to fluster you there.
What was I saying? Yeah, I mean, the whole idea behind these improved equations, as complicated as they seem, the goal is to actually make things simpler, so that once you set things up, you should be able to have the same tolerance for all of your colors and not have to adjust one. Anytime you get a new color in, you can just apply the same tolerance as you have to all the other colors. So that's of course the goal, the whole idea behind all of this, to make your visual color differences homogeneous across the color space. I will mention, just because I just did a webinar on this yesterday, that when measuring very, very dark colors, deep black colors, if you need to quantify the blackness or the darkness of the color, the jetness is often the term you hear, that does require a special instrument that has very, very, very good precision at the very low reflectance range, which is of course what you're doing when you're measuring blacks. The reflectance is very, very low. And I'll just mention that's our new Spectra 2 Guide Pro device. So yes, John, if you do get into the very, very, very dark color range where you really need to quantify how black your color is, that actually requires a whole different device. But for the most part, no, these equations are capable of handling any color you can throw at it. Okay,
that sounds good. If anyone wants additional information on that new jetness device, you can go to bic-instruments.com, just the website. It's up there, and you can check it out, or specific questions. You see Corey's email address right on the screen there, corey.cohen@altana.com. Feel free to contact him directly, or reply to any of the marketing messages you get, and we can direct them to the right person. So
John, you cut out.
No, you there? Can you hear me now? Can you hear me on? Okay,
I
now?
can hear you, John.
Okay, good deal. Good deal. Okay, so for tolerancing, then just kind of as a follow up to the last little bit, for tolerancing, you don't need necessarily tighter tolerances for dark colors.
I'm sorry, say that again, John.
You don't necessarily need tighter tolerances for dark colors. Once you set those tolerances, they would apply to all your colors. Is that right?
Yeah, because the equations are automatically going to account for that. So dark colors tend to have a smaller visual tolerance than lighter colors or more chromatic colors, but that's already going to be accounted for in the equation. So it's all kind of tied up in there, and you don't have to worry about it.
That sounds good. I appreciate it. I need some water here. Cool. So what other questions does anybody have, or anything we can assist with? Or if anyone wishes to be unmuted, let me know that too. Here's a random question for you, Corey. How many samples are recommended that a person take, or are there too many or too few that you would or would not recommend?
If you're referring to how many samples to evaluate when setting up your tolerances,
correct.
You really can't have enough. I want to say the number I remember hearing was at least 20. 50 would be better. 100 would be better than that. The more samples you use, the more data you're going to get, and sort of the more precise your tolerancing is going to be. I will say one important thing is to have try to get some samples from a few different production lots. Because if you have one production lot and maybe all the samples in that one lot were a little bit yellow, and that's it, that's what you're going to base your tolerances on. And the next batch that comes, just a little bit blue is even though it's visually acceptable, will be out of tolerance. So it's best to get samples from different production lots that will encompass different parts of sort of color space, or the deviation from the standard.
Yeah, that makes sense. Then you're not locked into one specific. You're taking a systematic sampling of everything out there. Good. Doesn't seem to be any more questions. If there's anything else here, otherwise we can wrap up. Like I mentioned, another question in here. What was the name of that software that I should use again? Is that Smart Chart?
The software, yes. So all of our instruments come with our Smart Chart software, and that's what allows you to choose all the different color equations that I mentioned before.
And that ties everything together, no matter what instrument you have, right? Yep.
Cool. Pretty much all of our instruments use it. So it's all your data from the, gloss, color, haze, whatever, in the same software.
Nice. And we do have other seminars coming up. Be on the lookout for those invitations. I think we do have one on Smart Chart reporting. Also, take a look at our YouTube channel. We have we're keeping the archives of these office hours and our normal 60 minutes web seminars up there, as well as there is a Smart Chart kind of tutorial there. We have, I think, 20 or 30 clips on specific things. So take a look at that on YouTube. You can just search on, BIC, color appearance and physical test solutions. So take a look there. I'll get the URL out to everybody. But thank you, Corey. Thank you for all the to all the attendees. Glad to have you here. Hope you learned something. And as always, reach out to any one of us if we can assist. And have a great rest of your day. Thank you.
Take care, guys.